Up until this point, we've been looking at the global average conditions on worlds. But now we should consider how atmospheric conditions vary from place to place on a planet. This means we need to start looking at climate and weather. First, a couple of definitions. Weather is a description of the moment-to-moment conditions at a given location on a world. On the other hand, climate is a long-term average of these conditions. Planetary climate and weather can be a hugely complex topic, so we're only going to look at a few of the broad processes that are important here. Many things can play a role in climate and weather. Some of these include latitude, season, and local topography, as well as the presence of water or other substances that can behave like water on the surface or in the atmosphere. One thing to keep in mind is that most of the processes that we associate with weather and climate happen mainly in the troposphere. This is largely because convection happens in the troposphere. Convection plays a big role in generating winds as well as creating the conditions where clouds can form. The first major topic dealing with climate is seasons. Near the beginning of the term, we looked in detail at how seasons occur on the Earth and most other planets. We saw that the Earth's distance from the Sun doesn't change significantly, so seasons depend only on the tilt, which in turn affects the angle at which the Sun's light hits the ground. So over the course of a year, the northern and southern hemispheres go through very similar seasonal patterns, separated by half a year. When it's warm in the northern hemisphere, it's cool in the southern hemisphere, and vice versa. However, there are some worlds whose distance from the Sun does change significantly over their orbits. On Mars, the distance changes by 20% over a year, while for Pluto, the farthest distance is 80% more than the closest distance. In comparison, the Earth's distance only changes by 3%. For worlds like this, we can't understand seasons unless we take both tilt and distance into account. Have a look at this diagram of the seasons on Mars. The eccentricity of the orbit is exaggerated, but the idea is correct. When the planet is closest to the Sun, the southern hemisphere is tilted towards the Sun, while the northern hemisphere is tilted away. When the planet is farthest from the Sun, these are reversed. The southern hemisphere is tilted away, and the northern hemisphere is tilted towards the Sun. The effect of this is to make the experience of seasons very different in the two hemispheres. In the south, distance reinforces the effects of tilt, making the seasons more extreme. When the South Pole is tilted away, the planet is also farther away from the Sun, so the winter is very cold. When the South Pole is tilted towards the Sun, the planet is also closer, so the summer is, by Martian standards, quite warm. On the other hand, the northern hemisphere has relatively mild seasons. When the North Pole is tilted away from the Sun, producing winter, it's also at its closest approach to the Sun, so the winter is warmer than in the south. Similarly, when the North Pole is tilted towards the Sun, the planet as a whole is farther away, so the northern summer is relatively cool. So while on Earth, distance from the Sun doesn't matter much for seasons, on some worlds, distance plays a larger role. But even in these cases, you still have to take tilt into account as well. A planet's eccentricity and tilt can change slowly over time because of the effects of other planets and moons tugging on them. As a result, the seasonal changes we experience now may not hold over longer timescales. Here on Earth, the tilt and orbit change over periods of 20,000 to 100,000 years. This slow change seems to be connected to a phenomenon we call ice ages. This plot shows the average temperature on Earth over nearly 1 million years. While we are currently in a warm period, for much of this time, the temperature was 6 to 10 degrees cooler. During these cooler periods, glaciers up to 4 kilometers thick expand over large areas of continents. As this map shows, during the last ice age, there were glaciers covering the northern half of North America, as well as sections of Europe and Asia. An ice age causes several things to happen to the Earth. With so much water locked up in ice, there's less water in the oceans, so sea level is much lower. We see evidence of this in the form of old shorelines that are now underwater. The weight of the ice causes continents to be compressed. Even though the last ice age ended around 10,000 years ago, we can still measure the ground rising as areas of Canada and Scandinavia are rebounding from this compression. And of course, these glaciers produce large-scale features on the ground. One familiar example of such a feature is the Yosemite Valley in California, a large glacial valley that was once filled with ice. Long Island in New York is a set of terminal moraines, the piles of rock and other debris that build up at the front side of a glacier. In this case, geologists can trace which mountains in New England these rocks came from. Even Niagara Falls is a glacial feature. The Niagara River passes over a large cliff known as the Niagara Escarpment. This escarpment extends across northern New York State and southern Ontario, and it also marks the southern edge of a glacier. Note that only a few degrees difference in average global temperature is required to make this tremendously different climate on the Earth. Now we'll look at another aspect of weather and climate: winds. We know that air pressure changes with altitude in a planet's atmosphere. However, even at the surface, the air pressure isn't always the same everywhere. This is directly related to convection. When warm air is rising, it creates a low-pressure region right at ground level, since the rising air is leaving a gap behind it. Similarly, when cool air is descending, it creates a high-pressure region. Winds develop when air flows from high-pressure to low-pressure regions, as shown below. The model you should have picked is what we call a Hadley cell model. It's a simple model of how air circulates on a planet. Air rises at the equator where it's warm and sinks at the poles where it's cold. This causes a low-pressure zone on the surface that draws air towards the equator, while at higher altitudes, air flows back to the pole, creating a closed circulation loop. This not only carries air back and forth from the poles to the equator, it also carries heat from the equator to the poles, keeping the poles from getting as cold as you would expect just from the amount of sunlight they receive. This simple model is actually a very good description of how heat flows in some atmospheres, like those of Venus, Mars, and Saturn's moon Titan. However, it doesn't work for the Earth or for the Jovian planets, so we need to look at why. The next key to understanding wind motions is called the Coriolis effect. The Coriolis effect happens on any spinning object. Imagine you're standing on a large spinning table. The outer edge of the table has to move much faster than the center. This is because the outer edge has to make a much bigger circle than the center in the same amount of time.
If you stand at the outer edge, then roll a ball towards the center, you'll notice something funny happening. Rather than rolling straight to the center, the ball will seem to turn in a sideways direction. This is because the ball still has the rapid rotational motion of the outer edge of the table. As it gets closer to the center, it's going faster around than the piece of the table it's sitting on. As a result, it turns in the direction of the spin. A similar thing happens if you roll the ball from the center towards the edge. In this case, the ball is going slower than the piece of the table it's sitting on, so it lags behind and turns in a direction opposite to the spin direction.
On a spinning planet, the same thing happens, with the poles acting like the center of the table and the equator acting like the edge. Anything moving from the poles to the equator or vice versa will be deflected in an east-west direction.
The Earth is an example of a world where the Coriolis effect is large enough to affect global wind circulation. The reason is similar to the ball in the spinning table. Air from the equator has a hard time mixing with air from the poles because equatorial air still has rapid rotational motion. This causes the large global circulation cells we described earlier to break up into several smaller cells. Air moving away from the poles is diverted westward, while air moving away from the equator is diverted eastward. So the air's simple up and down north and south convection cycles become more complicated. The spin of the Earth gives air the energy to travel along spiral paths that go alternately east and west at different latitudes. At the Earth's surface, the east and west motion can be seen in the alternating directions of the prevailing winds at different latitudes. Notice also that this causes alternating regions of rising and descending air at different latitudes. This is detected from the surface as regions of higher and lower air pressure and characteristically different weather. We'll come back to this shortly when we talk about clouds.
These different wind directions have played a big role in human history. For example, the entire Atlantic trade circuit during the era of sailing ships was based on this. To travel from Europe, a sailing ship first had to sail south to Africa to pick up the westward moving winds. These carried the ships to the Caribbean. From there, those ships could travel north along the North American coast, where they could then go back across the ocean on the eastward moving winds. The Coriolis effect can also play a role on slightly smaller scales. When warm air rises to create a low-pressure region, the air around it will flow into this region. However, if the Coriolis effect is strong enough, then the air flowing in will be deflected into a circular motion instead. This circulation will be opposite in opposite hemispheres, counterclockwise looking down on it in the northern hemisphere, and clockwise in the south. We see this in the motion of hurricanes and other large storms that develop as a result of warm rising air. Now we turn to the last section on climate, clouds. Clouds are made up of droplets of liquid or crystals of ice that are small enough to be held up by the atmosphere. Though clouds aren't made of gas, they are condensed out of the gases in the atmosphere. However, they can only be trace gases, not the main components of the atmosphere. If it was cold enough for the main gases to condense, there'd be nothing to hold the cloud up, and it would form a frost layer on the ground instead. Examples of clouds include water vapor on the Earth and Mars, sulfuric acid on Venus, methane on Uranus and Neptune, and ammonia compounds on Jupiter and Saturn. The way clouds form is through condensation. When a parcel of air cools down, a gas, like water vapor, starts to form tiny liquid droplets. This cooling can happen at night, which is why fog often forms at night, or when warm, moist air mixes with cooler air. However, one of the key ways to cause a cloud to form is when air near the surface rises due to convection and cools. This is common in the troposphere. Clouds can only form when the air is cool enough for gases to begin condensing. Each gas has a different condensation temperature, so the gases that can condense will depend on the temperature of the atmosphere. In an atmosphere where several gases can produce clouds, the ones that condense at the coldest temperatures will be highest in the troposphere, while gases that condense at higher temperatures will be lower down in the atmosphere. In the inner solar system, where the temperatures are warmer, water and sulfuric acid form clouds. Further from the Sun, Jupiter and Saturn have clouds of ammonia, water, and some large complex hydrocarbons that can form hazes. Still farther away, methane condenses in the atmospheres of Uranus and Neptune. These worlds may also have water and ammonia clouds, but if so, they're too deep in the atmosphere to see. We know that clouds are made of tiny droplets or crystals held up by the air. If those drops or crystals get too big, the air won't be able to hold them up, and they'll start to fall. We call this process precipitation. Once they start falling, there's a much greater chance that they'll grow larger through collisions, just like the accretion process we described earlier in solar system formation. If there's an updraft caused by convection, then the droplets can get quite large before they break out of the cloud. Once these drops or crystals fall to the ground, we call them rain, snow, or hail. Remember, the clouds form where air rises. For that reason, the places where there's rising air are the wet parts of the globe, the tropics along the equator, and the temperate zones. That's why we have tropical rainforests in the Amazon, Central Africa, and Southeast Asia, as well as temperate wet regions in the Pacific Northwest of North America and Western Europe. There's also the stormy regions south of South America, Africa, and Australia, known as the Roaring Forties. On the other hand, areas of descending air are much drier. These are the subtropical deserts on either side of the equator, like the Sahara, the Namibian Desert, the Arabian Desert, the Gobi Desert, the American Southwestern Desert, and the Australian Outback. The polar regions are also very dry. Both Antarctica and the high Arctic get very little precipitation. The reason the ice is so thick on the Antarctic continent is because it never melts, not because it gets a lot of snow every year. These are the major climate zones on the Earth, the alternating regions of wet and dry conditions caused by the breakup of global circulation cells due to the Coriolis effect. Of course, this is only a starting point to understanding the Earth's climate, and there are clearly exceptions to the simple picture we've just given. The very wet American Southeast is an example where air and ocean currents break the pattern and cause a wet climate in an area you would predict to be dry based just on latitude. However, it's still useful to have this simple picture of climate zones so that we can better pick out the exceptions to the general rule. Even though Jupiter is a Jovian planet with an atmosphere made of hydrogen and helium, there are a lot of similarities between its atmosphere and the Earth's. First, the temperature structure follows the same pattern as the Earth, with a troposphere, stratosphere, thermosphere, and exosphere. In this case, much of the heating in the troposphere comes from the planet's own internal heat, rather than the sunlight warming the surface. Also, the stratosphere is formed because organic compounds in the atmosphere absorb ultraviolet light, rather than ozone. However, though the details are different, the basic physics and temperature structures this produces remain the same. As we've already seen, Jupiter has 3 layers of clouds in its troposphere rather than just one. The top ammonia clouds are white, while the ammonium hydrosulfide clouds below them are brown. We can see these 2 layers easily when we look at the planet. There are water clouds further down, but these are harder to detect below the ammonium hydrosulfide. Jupiter's ammonia clouds show a pattern similar to Earth's water clouds. Where the air is rising, ammonia clouds form. Where the air is descending, it's clear, and we can see through to the next layer down. Jupiter is a large planet with a much faster rotation than the Earth, so the Coriolis effect is much stronger on Jupiter. Just like on Earth, this means that north-south airflow is deflected into east-west airflow, giving the planet alternating climate zones of rising and descending air, which show up as alternating bands of white ammonia clouds and clear air with a view down to the brown ammonia hydrosulfide. This gives Jupiter its familiar striped appearance. This strong Coriolis effect means that east-west wind speeds on Jupiter are very high, while there's very little motion of air to the north and south. Any north-south wind is immediately twisted into an east or west direction. Finally, the Coriolis effect allows huge, powerful storms to develop. The Great Red Spot is a storm that's larger than the Earth. It's lasted for at least 350 years and probably much longer. Now let's see if you can put together all of what we've learned about atmospheric structure and weather so far. Here's some information about a hypothetical planet orbiting another star. Use the information given to see if you can answer the question and explain your answers. You'll have to focus on what causes the different parts of the temperature structure, as well as the processes that drive winds, clouds, storms, and climate zones.